Hello and welcome. In this video, we're going to talk about what a rational function is, what it looks like to graph a rational function in various forms. We're going to talk about wholes and vertical asymptotes and how those discontinuities affect our graph. And we're going to focus on how to graph in general for a rational function. So let's go ahead and jump right in. So what is a rational function? A rational function is a function with a polynomial over a polynomial. So for example, this says p of x over q of x, where p of x and q of x are polynomials, and q of x is not equal to 0 because we can't have 0 in the denominator of our fraction. So an example of a rational function would be something like x plus 5 over x minus 2. Or something like x squared plus 6x plus 1 over x plus 4. Those are examples of rational functions. So polynomial over polynomial, that's what we're talking about. When we graph the parent function of a simple rational function, so the simplest form, the parent function of rational functions, is f of x is equal to 1 over x. And the shape that this makes, these sort of two little, they're called branches, but they sort of look like exponential graphs, two little graphs off to the side, is called a hyperbola. And you'll learn more about graphing different types of hyperbolas in future classes. In this class, we're really just going to focus on how do we graph a rational function using the asymptotes and any holes that may occur. So if there is a value that would make a function undefined, like here, this would be undefined if there was 0 in the denominator, meaning it would be undefined if x was equal to 0. This function here would be undefined if we had 2 in for x, because that would make 2 minus 2, 0. This function down here would be undefined if x was equal to negative 4, because then the denominator would become 0, and we can't have something over 0. So that means at each of those values, so here we said at x equals negative 4, here we said at x equals 2, and here we said at x equals 0, at all of those values we would have vertical asymptotes. So vertical asymptotes occur for values of x that would make the denominator equal 0, which would make the function undefined. But what would happen if we had a function where the numerator and the denominator had a term in common? So what would happen if we had x plus 2 over x plus 2 times x plus 1? So if I asked you what two x values would make the denominator 0, hopefully you would be able to tell me that it would be 0 if x is equal to negative 2, and it would be 0 if x is equal to negative 1. But what happens in the numerator if x is equal to negative 2? If we plugged negative 2 in for x, we would have to plug it in here, here, and here, which would mean the numerator would be 0 and the denominator would be 0. So instead of having a number over 0, we'd have 0 over 0, which is called indeterminate form, and that's something you'll learn about in future classes. What I want you to notice in this class, that we actually have an x plus 2 factor in the numerator and in the denominator, which means we can divide that factor out. When that factor divides out, it's called a hole in the graph. And I'll show you what that looks like in the graph in just a minute. But the key thing is a hole happens when the factor divides out. So a vertical asymptote is an x value that makes the denominator of your rational function 0. A hole occurs when we have a factor that divides out that originally would have been a domain restriction, that originally would have given you 0 in the denominator of the fraction. So what you'll notice in this graph here is that we have this vertical asymptote at x equals 0. But there's also another asymptote in this graph. There's one that's happening here horizontally, a horizontal asymptote of y equals 0. To find horizontal asymptotes, we first need to look at how the function is behaving. So if the degree of the numerator and the degree of the denominator are the same, then we can just divide the coefficients. So again, if the degree of the numerator and the denominator are the same, so they're both x, or they're both x squareds, then you're just going to divide the numbers in front. So in this case, we would divide 2 and 1 to get y equals, because horizontal lines are equations, y equals 2. If the degree of the numerator is exactly 1 less than the degree of the denominator, so for example, x plus 1 over x squared plus 5, then there is a horizontal asymptote at y equals 0. And those are really the two kinds of rational functions you might see, where the degrees are the same and you're dividing the leading coefficients, or where the degree of the numerator is exactly 1 less than the degree of the denominator, in which case we will have a horizontal asymptote at y equals 0. There are other options, but you'll learn about those more in future classes. So let's look at an example that has a handful of these different things going on within it. So here we have the function f of x equals x plus 2 over x squared minus 4. So we know that we can factor that denominator to get x plus 2 and x minus 2 in the denominator. So if I asked you right now what x values would make the denominator 0, hopefully you could tell me that the denominator would be 0 if x was positive or negative 2. What I want you to notice is that we actually have a factor in the numerator and the denominator. We have the factor x plus 2. If we divided that factor out, now instead of having a vertical asymptote, since that factor divided out, we're going to have a hole at the x value that would make that factor 0. So at x equals negative 2. We will still have a vertical asymptote at the value that didn't cross out. So what makes this denominator 0? That would be 0 when x is equal to positive 2. Now, here, if we look at our horizontal asymptote, so if we're looking at dividing the coefficients, after we have simplified this, we now, or even if you look back up here, the degree of the numerator is exactly 1 fewer than the degree of the denominator, so we have a horizontal asymptote at y equals 0. What I want you to notice, and this is a really big idea, is that our original function, this original function, is exactly the same as this function here, as long as we aren't talking about the value that we crossed off when x is equal to, not positive 2, when x is equal to negative 2. If you graphed this function and you graphed this function, they would be exactly the same everywhere but at this point. The only difference at that point is there would be a hole. So you can see an open circle in the graph down here. That open circle will occur at the value if we plugged negative 2 in here. So if we plugged negative 2 into this function, we would get negative 1/4. So there would be a hole in the graph at negative 2, negative 1/4, which is this coordinate right here. So I know this is a lot to take in, a very different kind of function than we have looked at, but let's really focus on first just understanding the holes and the asymptotes, and then we can tie that back to how do we use that information to create a graph on our own. Okay, so typically the first thing we're going to do if we're looking at graphing a rational function is we're going to factor. And on number 1, that's already been done for us. Now we're going to look to see if any of the factors are both in the numerator and the denominator. So here, x minus 3 is both in the numerator and the denominator, which means that is going to divide out. And the x value that would make that factor 0, there's going to be a hole in the graph at x equals 3. So our original function f of x could be rewritten as just the two factors that have not divided out, as long as we also state that x is not allowed to be 3. So again, the big idea in this section, this function is exactly the same as this function as long as x is not equal to 3. Well, what would happen if x was equal to 3 and we plugged that into this function? That's where the hole in the graph is going to be. That's where on the graph we would have an open circle. If we plug 3 in there, we're going to get 3 plus 2 is 5 over 2 times 3, 6 plus 1, 7. So there's a hole in the graph at the point 3, 5 over 7. Everywhere else, this value is exactly the same as if you plugged the same x value in here. The functions are the same. Now, our vertical asymptotes are the x values that would make our denominator 0. So what would make our denominator 0? 2x plus 1 would be 0 if x was equal to negative 1/2. To find our horizontal asymptotes, we divide the coefficients in front of our x's. So both of our x's are first degree. So there's an invisible 1 in front of that x, a 2 in front of the x in the denominator. So there's a horizontal asymptote when y is equal to 1/2. All right, I want you to pause the video and see if you can factor number 2 on your own, and then see if you can identify any hole or asymptote. Then unpause the video and see how you did. So here I have factored. The hole occurs at the x value that divides out. In this case, x plus 1 divides out, and that is 0 if x is equal to negative 1. So my new function would be x minus 1 over 2x minus 1 as long as x is not equal to negative 1. To find the y-coordinate of the hole, I'm going to plug negative 1 into my new function. If I plug in negative 1, I'm going to get negative 2 over negative 3, which is going to give me positive 2/3. Now looking at that function, I can identify my vertical asymptote, which is any x value that makes the denominator 0. What x value makes this denominator 0? When x is positive 1/2. To find the horizontal asymptotes, that's going to happen at y equals, we're going to divide the leading coefficient since the degree of the numerator and the degree of the denominator are the same. So that's going to give us y equals 1/2. Okay, I want you to pause the video and see if you can work through number 3 all the way on your own, and then unpause the video and see how you did. All right, hopefully you had time to work through that on your own. The denominator factors to x plus 1, x minus 1, and our x minus 1s are going to divide out. So there is a hole when x equals 1 because 1 would make both the numerator and the denominator equal 0. So here's our simplified function for x not equal to 1, but if x does equal 1, where is the hole in our graph? The hole in our graph is at 1, 1/2. Now looking at this much simpler function, horizontal asymptote occurs when we divide the coefficients. Vertical asymptote occurs when we consider the x value that makes the denominator 0. So the denominator is 0 if x is negative 1. The degree of the numerator and the denominator are not the same because there's no x in the numerator. That means we're really saying 0 over 1, so we're going to have a horizontal asymptote when y equals 0. Now don't worry, we're going to keep reviewing this idea as we build on it a little bit and begin to graph. Okay, I'm going to encourage you again to pause the video. Don't worry about any of the graphing right now, but see if you can identify whether or not there are any holes and where the horizontal and vertical asymptotes are. Then unpause the video and see how you did. Okay, so no factors divide out, so there aren't any holes. The vertical asymptote occurs for the x values that make the denominator 0. In this case, that's going to be x equals negative 2. The horizontal asymptote occurs when we divide the leading coefficient. And now we're just going to add both of those things to our graph. So a dotted vertical line at x equals negative 2, a horizontal dotted line at y equals 3. So now we have identified and graphed our asymptotes. What we need now are to graph the branches, and the branches for the types of rational functions we're going to be graphing are always going to be diagonal from each other. So what we need to do is we need to pick some x values that are to the left of this vertical asymptote and to the right of this vertical asymptote. Then we just need to plug those x values into our function up here, and figure out what the value of the function is. So I'm going to ask that you always plug in at least 3 values per branch. So that would give you a minimum of 6 points that you're going to be plotting. That when you connect, you make sure you have a smooth curve and you don't cross those asymptotes. And then after you graph, you're going to state the domain and the range. So I'm going to put x equals negative 2 kind of in the middle here, because I need to pick 3 numbers that come to the left of that. So -3, -4, -5, and then at least 3 values that come to the right, -1, 0, and 1. Okay, I'm going to have you go ahead and plug in each of those values. So f of -5, f of -4, f of -3, f of -1, f of 0, f of 1. Pause the video and plug all of those values into this function and write down what you get when you do that. So fill in your table. Then unpause the video and see how you did. So hopefully you had time to plug those values in. Really, you can show as much or as little work as you need to get those values, but you need to be able to plug numbers in and simplify. So give yourself the time to do that. Now let's plot these points. -5, 16 over 3. Well, I know that 15 over 3 is 5, so this is going to be a little bit more than 5. -4, 13 over 2 is -4, 6.5, and -3, 10. So I'm going to plot those 3 points first. So there I have my 3 points. Now I could keep finding points if I wanted my graph to be more precise. I could plug in -6, I could plug in -7, -8. But all I really want you to do here is get the idea of the curve. We're going to go towards our asymptotes on either side. Now the other part of my graph should be down in this quadrant, because each piece is going to be diagonal from each other for the types of rational functions that we're graphing. So go ahead and plot the 3 points, -1, -4, 0, -1/2, and 1 2/3. And then connect those points to make a smooth curve that is approaching our asymptotes on either end. So you're always going to start by identifying, is there a hole, which means you may have to factor first. What are the horizontal and vertical asymptotes? You're going to use those to make a table, plug in values, and then graph. Now let's talk about the domain and the range. Every x value is going to be covered at some point except for the one on the asymptote. So really all real numbers except for -2. In interval notation, we write that as -∞ to -2 and -2 to infinity. So everything except -2. Similarly, for the range, the only y value we're never going to cross is y equals 3. There's a horizontal asymptote there. So we're going to write -∞ to 3 and 3 to infinity. Let's look at some more examples. Okay, let's actually start by factoring number 5 together. This is going to factor to x plus 4 times x minus 2 over x minus 2 times x plus 1. Now, before we even jump into graphing, I want you to first identify whether or not there are any holes and what the asymptotes are, and then graph those asymptotes on your graph as dotted lines. So go ahead and pause the video and do that on both number 4 and number 5. All right, so on number 4, there's no hole. There's a vertical asymptote when x equals 3 and a horizontal asymptote when when y is equal to 2. So when we make our table, we know the number that we have to go to the left and the right of is our asymptote, which is at x equals 3. So we can look at 2 and 1 and 0, and we can look at 4, 5, and 6. So go ahead and pause the video and plug those values into your function to find the output values, and then go ahead and plot those points and connect them. Then unpause the video and see how you did. So here I've plotted the points on both sides that I just calculated, and then I'm going to connect them and make it curve and get closer to each of these asymptotes. So there we go. What would the domain of this function be? Well, the domain is going to include every x value except for the one on the vertical asymptote, so -∞ to 3 and 3 to infinity. The range is going to include every y value except for the horizontal asymptote, so -∞ to 2 and 2 to infinity. For number 5, after we factor, we can identify that there's a hole. There's a hole in the graph when x equals 2 because the x minus 2 factor divides out, which means we can rewrite our function g in a much simpler way as long as we note that x is not allowed to be 2 because that's the factor that divided out. If x is 2, if we plug 2 into this function, it gives us the coordinate for our hole. So that would be 6 over 3, which is 2. So that's why we have an open circle on our graph at the point 2, 2. There's a hole in the graph at that point. Now, when we make the table, we're still going to be looking at that vertical asymptote. So we need to pick values like -2, -3, and -4 for the left-hand side, and 0, 1. I'm going to just make a note there's a hole at 2. So 0, 1, and 3 for the right-hand side. When you plug those values in, you could plug them into the original function if you want to. Or, since none of those values are 2, you can plug it into the simplified function, which is going to make the math a lot faster. So go ahead and pause the video and find out what happens when you plug each of these x values into your new simplified g of x function. So now I've completed my table and I've plotted those points. I'm going to connect and get closer to both of my asymptotes as I graph, making sure not to cross them. When I get to the hole, you need to make sure that you do not make your smooth curve cross the hole. It needs to be empty. That's the whole idea of having a hole. So make sure that the hole is open and that you're not crossing through it and that you're not crossing your asymptotes. So how does this hole affect the domain and the range? Well, the domain, there's now two x values that never happen. There's the two x values that never happen is that x is never equal to -1 and x is never equal to 2, the hole and the vertical asymptote. So when we list those, we always go smallest to largest. So we can go from -infinity to -1. Then we have a break from -1 to +2. Then we have a break. And then we go from 2 up to infinity. So each of these numbers is coming from a whole or a vertical asymptote. Similarly, with the range, now we're looking at the y values, -infinity to 1, and then 1 to the y value of that whole, which is also 2, and then the y value of that whole up to infinity. All right, we're going to work through two last examples together. The next one is going to be a little different. It's actually going to have a vertical translation, so we can see what happens when that occurs. And the last one is going to be a lot like number 5 here, and I'm going to encourage you to try that one all the way on your own. But let's do one more together first. All right, last two graphing problems. First thing I want you to notice is that there are no holes on number 6. There is no factor that divides out, and this is already as simplified as possible, so I'm just going to make that note to myself. Where is the vertical asymptote? That's right, it's at x equals -2 because that's the x value that makes the denominator 0. So I'm going to go ahead and add that to my graph. Now, if you think about the horizontal asymptote, that's what happens when we divide the leading coefficients. In this case, when we divide the leading coefficients, we get 0 since the degree of the numerator is 1 less than the degree of the denominator. But then we also have this -1, which is our vertical translation. What that means is that our horizontal asymptote is at 0, -1, 0 from this portion here, -1 from the translation. So we're going to have a horizontal asymptote at y equals -1. Let's go ahead and add that to our graph. Now, it's going to get a little bit more complicated when we're doing the math to find these values because every time we plug something into this portion, we then have to subtract 1. So go ahead and pause the video and set up and fill in your table, remembering that each time you plug in an x value, you're going to subtract 1 from the fraction portion. So here are the coordinates I calculated from my table when I plugged in my values. I'm going to go ahead and graph those points, connect them, and then identify the domain and range. Go ahead and pause the video and do that for yourself. So here I have my graph. Now, domain and range, if you didn't already get it, the domain is everything except -2. The range is going to be everything except -1. All right, I really want you to push yourself on number 7. Factor, identify any holes, the x and y coordinate, identify any horizontal and vertical asymptotes, make your table of values, and graph those points. And then don't forget to state the domain and range. See how far you can get on your own. All right, so hopefully you were able to get started. I have identified that there's a hole at x equals -4. If I plug -4 into my new function, I get -6 over -1, so +6. So I'm going to have a hole at the coordinate -4, 6. After I simplify, I can identify my vertical asymptote, x equals -3, and my horizontal asymptote, dividing the coefficients, y equals 1. Now I want you to go ahead and make your table of values. So here are my coordinates. Now I'm going to plot them. And now we have our graph. Domain, if you haven't already done it, -infinity to the whole, that's the first discontinuity. So that's at -4. -4 to our asymptote, -3, and then -3 forever to infinity. Range, -infinity to the first discontinuity up and down, which is at 1. Then 1 to the y value of that whole, which is 6, and then from 6 up to infinity. So a lot to process and digest in this section. First of all, the difference between a whole and a vertical asymptote. When a factor divides out, it's a whole. When it doesn't divide out, the values that make the denominator 0 are our vertical asymptotes. We talked about how to find the horizontal asymptotes by dividing our leading coefficients if we have a numerator and a denominator that are the same degree, how to sketch those things, and then really just make a table of values using at least 3 points to the left and to the right of our vertical asymptote to get an idea of the shape. So go ahead and write down any questions you have, and I look forward to supporting you on this. Thanks for listening.